Tonight I'm going to show you about a new kind of force. So take a look at this picture. We've got a rock at the bottom of a jar of water. Okay? And up at the top we talk about water displaced, but I'll get to that in a second. I want to draw your attention to this free body diagram over here, where I have weight, which should be familiar to you. We're on Earth. The rock has weight. It has a normal force. It's sitting on the bottom of the jar, so there's a normal force. And I've also labeled this thing called the buoyant force. Now the rock's not moving, so all of those forces add to zero. The up forces equal the down forces. But this FB, that's called the buoyant force. And the buoyant force occurs whenever an object is in a fluid. So this rock in water, the water is actually pushing that rock up. Which you might think, well, then why doesn't the rock float up? What it does is it just decreases the amount of normal force needed to counteract gravity, so the rock isn't falling down. And it's not just the normal force holding that rock up, it's called the buoyant force. Something we're going to talk about tonight is whenever there is a buoyant force, there must be water that has been displaced or moved. So water that's been moved from its original place. When I dropped this rock in this jar of water, the level of the water before I dropped it was right here. When I dropped the rock in, the water level went up this much. Anytime there is a buoyant force, FB, it means that some water has been moved or displaced. We're going to talk more about that throughout the rest of this video, so don't worry if that's not super clear at the moment. One thing we can do is actually measure the amount of water that rock displaced. So this time in the experiment, I took a jar and filled it up with water. So before the rock was in it, it was full. And then I set this other smaller jar down beside the big jar. And when I dropped the rock in, or lowered it in with this string, some of the water came out of the glass and now is in this other cup. So we could actually see how many milliliters of water was displaced. So this is my displaced water. Now because some water was displaced, I also know that there is a buoyant force supporting that rock. Whenever you insert an object into water, some of the water moves out of the way, and that water moving out of the way creates a force in response to that rock. Here on the free body diagram we would have weight, the force of tension since that rock is being held by a string, and the buoyant force. And the up forces would add to equal the down force. Now we're about to put all this together. There's an idea called Archimedes Principle, devised by a guy named Archimedes several hundred years ago. He said that the buoyant force is equal to the weight of the displaced liquid. So, if we know how much water was displaced when I dropped the object into the water, and we weigh that water, so over here, we're using the scale to weigh the water, the weight of the water that was displaced is equal to the amount of force that the water still in the jar is giving to that object. And so we can use this principle to actually calculate buoyant force. We can find the weight of the displaced liquid, and then we know that's how much force the liquid is putting on the object that's been inserted into it. I've intentionally made this first video kind of short because this idea might be a little confusing. So if you don't feel confident in this right now, please watch the video again and try to understand it a little better. The big takeaway is, whenever you insert an object into a liquid, the force the liquid pushes back, so the buoyant force, is equal to the weight of the water that the object shoved out of the way. Buoyant force is equal to the weight of the displaced liquid. Again, if you need to watch this video again to understand that, please do so.